The light hitting your eyes from the Andromeda Galaxy began its journey when our earliest human ancestors were learning to walk upright. For 2.5 million years, those photons have been racing through the void at the speed of light, carrying a message about a galaxy so massive it defies comprehension. But here's the cosmic joke. By the time that ancient light reaches us, it's showing us less than 5% of what Andromeda actually is. To understand just how big Andromeda really is, we need to start with what we can see with our naked eyes. That faint patch of light you might glimpse on a dark night represents only the galaxy's bright central core, what astronomers call the bulge. This region alone contains hundreds of billions of stars packed into a space roughly 20,000 light-years across. To put that in perspective, if our entire Milky Way galaxy were the size of a dinner plate, Andromeda's central bulge would be like a serving platter. But that's just the beginning. The Andromeda Galaxy, officially designated Messier 31, or M31, stretches far beyond what our eyes can detect. When astronomers use sensitive instruments to map the galaxy's full extent, they discover something remarkable. Andromeda's spiral arms and outer regions extend much farther into space than the bright core suggests. The galaxy's visible disk, the part containing most of its stars, spans approximately 220,000 light-years from edge to edge. Think about that number for a moment. Light, traveling at 186,000 miles per second, takes 220,000 years to cross Andromeda from one side to the other. If you could somehow travel at the speed of light, the fastest possible speed in the universe, it would take you longer to cross this single galaxy than modern humans have existed on Earth. We're talking about distances so vast they make interplanetary travel look like a walk around the block. The Hubble Space Telescope has been instrumental in revealing Andromeda's true scale. Since its launch in 1990, Hubble has captured thousands of images of our galactic neighbor, each one revealing new details about its structure and size. In 2015, astronomers used Hubble to create the largest and most detailed image of Andromeda ever taken, a mosaic containing over 1.5 billion pixels that shows individual stars across a significant portion of the galaxy. What Hubble revealed was breathtaking. Andromeda contains approximately 1 trillion stars. That's 1,000 billion individual suns, each potentially hosting its own family of planets. To put this in perspective, if you could count one star every second, it would take you over 31,000 years to count all the stars in Andromeda. The galaxy contains more stars than there are grains of sand on all the beaches of Earth. But even these mind-boggling numbers don't tell the full story of Andromeda's size. Recent observations have revealed that the galaxy is surrounded by an enormous halo of dark matter and sparse stars that extends far beyond the visible disk. This halo, invisible to the naked eye but detectable through careful astronomical observations, may stretch as far as 600,000 light-years from the galaxy's center, nearly 3 times the diameter of the visible galaxy. The discovery of Andromeda's extended halo came from painstaking observations of distant stars and stellar streams, long trails of stars that have been stripped from smaller galaxies as they fell into Andromeda's gravitational embrace. These stellar streams act like cosmic breadcrumbs marking the outer boundaries of the galaxy's influence. The Sloan Digital Sky Survey and other large-scale astronomical projects have mapped dozens of these streams, revealing the true extent of Andromeda's gravitational domain. When we include this extended halo, Andromeda becomes truly colossal. The galaxy's total diameter may exceed 1 million light-years, making it roughly 5 times larger than our own Milky Way. If Andromeda were a city, the bright central region we can see would be like downtown, while the extended halo would encompass suburbs stretching to the horizon and beyond. The mass of Andromeda is equally staggering. Astronomers estimate that the galaxy contains approximately 1.5 trillion times the mass of our Sun. Most of this mass isn't in stars, it's in dark matter, the mysterious substance that makes up about 85% of all matter in the universe. Dark matter doesn't emit light, so we can't see it directly, but its gravitational effects shape the structure and evolution of galaxies like Andromeda. If these cosmic scales are already stretching your imagination, make sure to hit that subscribe button and give this video a thumbs up. We're just getting started on this journey through Andromeda's incredible dimensions, and trust me, the discoveries get even more mind-blowing from here. To truly appreciate Andromeda's size, let's compare it to some familiar cosmic landmarks. Our solar system, from the Sun to the orbit of Neptune, spans about 60 astronomical units, roughly 5.5 billion miles. That sounds enormous until you realize that Andromeda's diameter is about 4 billion times larger than our solar system. If our solar system were a marble, Andromeda would be larger than the entire state of Texas. The distance between Earth and our nearest star, Proxima Centauri, is about 4.2 light-years. You could fit over 50,000 of these interstellar distances across Andromeda's diameter. The galaxy is so large that light from one edge takes longer to reach the other edge than complex life has existed on Earth. When light left one side of Andromeda during the Cambrian explosion 540 million years ago, it's just now reaching the other side. Recent studies using the Gaia Space Telescope have provided even more precise measurements of Andromeda's structure and motion. Gaia, launched by the European Space Agency in 2013, has been mapping the positions and movements of over 1 billion stars in our cosmic neighborhood. Its observations have revealed that Andromeda is not just large, it's also incredibly complex, with multiple spiral arms, stellar streams, and satellite galaxies all interacting in a cosmic dance that has been ongoing for billions of years. The galaxy's spiral structure adds another layer to its impressive scale. Andromeda has at least 2 major spiral arms that wind outward from the central bulge, along with several smaller arm segments and spurs. These spiral arms aren't solid structures, they're density waves that sweep through the galaxy, triggering star formation as they compress gas and dust. The spiral pattern rotates more slowly than the stars themselves, creating a dynamic, ever-changing structure that has persisted for billions of years. The spiral arms of Andromeda stretch across the galaxy's entire disk, creating a pattern that's both beautiful and scientifically fascinating. Each arm contains billions of stars, vast clouds of gas and dust, and active star-forming regions where new suns are being born. The Perseus arm alone, one of Andromeda's major spiral features, contains more stars than exist in many entire galaxies. These arms aren't just decorative, they're the galaxy's stellar nurseries, where the raw materials of space are transformed into the building blocks of solar systems and potentially life itself. What makes Andromeda's scale even more impressive is how it compares to our own cosmic home. The Milky Way, which seems impossibly vast from our perspective here on Earth, is actually the smaller sibling in this galactic pair. I explored just how tiny we are within our own galaxy in my video, How Small Are We Inside the Milky Way? And the perspective is both humbling and awe-inspiring. But when we zoom out to compare the Milky Way to Andromeda, we discover that our entire galactic home would fit comfortably within Andromeda's boundaries with room to spare. The link is in the description and pinned on the comments. The mass difference between these two galaxies is particularly striking. While the Milky Way contains an estimated 400 billion to 1 trillion stars, Andromeda hosts approximately 1 trillion stars, making it potentially 2 to 3 times more massive than our home galaxy. This mass difference has profound implications for the structure and evolution of both galaxies, and it will play a crucial role in their eventual collision about 4.5 billion years from now. Speaking of that future collision, the scale of Andromeda becomes even more mind-bending when we consider the cosmic choreography currently unfolding. Right now, as you're watching this video, Andromeda is racing toward us at approximately 250,000 miles per hour. That might sound terrifyingly fast, but given the enormous distances involved, this galactic encounter will unfold over billions of years, a slow-motion cosmic ballet that will reshape both galaxies. The Hubble Space Telescope has been tracking this approach with remarkable precision. By measuring tiny changes in the positions of stars within Andromeda over many years, astronomers have been able to calculate not just the galaxy's approach speed, but also its rotation and internal motions. These observations reveal that Andromeda isn't just a static collection of stars, it's a dynamic, evolving system where stellar orbits, gas flows, and gravitational interactions create an incredibly complex three-dimensional structure. One of the most remarkable aspects of Andromeda's size is how it challenges our understanding of galaxy formation and evolution. Galaxies this large shouldn't exist according to some early theoretical models. The process of assembling 1 trillion stars into a coherent structure while maintaining spiral arms and avoiding gravitational collapse requires a delicate balance of forces that astronomers are still working to understand fully. The galaxy's supermassive black hole adds another dimension to its impressive scale. At Andromeda's center lurks a gravitational monster containing approximately 140 million times the mass of our Sun. This black hole is about 35 times more massive than Sagittarius A star, the supermassive black hole at the center of our own galaxy. The event horizon of Andromeda's central black hole, the point of no return, would encompass an area larger than the orbit of Earth around the Sun. But even this supermassive black hole is dwarfed by the galaxy that surrounds it. The black hole's sphere of gravitational influence extends only about 13 light-years from the galactic center, a tiny fraction of Andromeda's overall size. This illustrates just how vast the galaxy truly is. Even an object massive enough to trap light itself is just a tiny speck within Andromeda's enormous structure. The galaxy's satellite system provides another perspective on its incredible scale. Andromeda is accompanied by at least 14 known satellite galaxies, smaller galaxies that orbit around it like cosmic moons. The largest of these satellites, Messier 32 and Messier 110, are substantial galaxies in their own right, each containing billions of stars. Yet they appear as mere companions when viewed alongside Andromeda's massive bulk. These satellite galaxies orbit at distances ranging from a few thousand light-years to several 100,000 light-years from Andromeda's center. The most distant satellites are so far away that they're barely held by the galaxy's gravity, yet they're still considered part of the Andromeda system. This extended family of galaxies occupies a volume of space several million light-years across, a cosmic empire that dwarfs anything in our local galactic neighborhood. Recent discoveries have revealed that Andromeda's influence extends even further than its satellite galaxies suggest. Streams of stars and gas connect Andromeda to its satellites and even to more distant galaxies, creating a web of gravitational interactions that spans millions of light-years. These cosmic filaments are so faint that they're invisible to the naked eye and can only be detected using the most sensitive astronomical instruments. The Panoramic Survey Telescope and Rapid Response System, known as PAN-STARRS, has been particularly valuable in mapping these extended structures. This ground-based telescope system has surveyed vast areas of the sky, revealing stellar streams, tidal tails, and other evidence of Andromeda's gravitational influence across enormous distances. These observations show that galaxies aren't isolated islands in space, they're connected by invisible threads of gravity that extend far beyond their visible boundaries. When we consider all of these factors, the visible disk, the extended halo, the satellite system, and the gravitational sphere of influence, Andromeda emerges as a truly colossal structure. The galaxy's total gravitational domain may extend as far as 2 million light-years from its center, creating a sphere of influence that encompasses a volume of space containing over 30 cubic million light-years. To put this in perspective, imagine shrinking the entire observable universe down to the size of Earth. On this scale, Andromeda would still be about the size of a large city. The galaxy is so vast that it contains more volume than 1 million spheres the size of our solar system. If every star in Andromeda had a planetary system like ours, the total number of planets would exceed the number of grains of sand on all the beaches and deserts of Earth. The sheer number of worlds that could exist within Andromeda's boundaries is staggering beyond comprehension. If we assume that even a small fraction of Andromeda's trillion stars host planetary systems, and recent discoveries by the Kepler Space Telescope and other exoplanet hunters suggest that planets are incredibly common, we're looking at potentially hundreds of billions of worlds within this single galaxy. Some of these planets might be rocky worlds like Earth, others could be gas giants like Jupiter, and still others might be types of planets that don't exist in our solar system at all. The James Webb Space Telescope has begun to revolutionize our understanding of galaxy formation and structure, and its observations of Andromeda are providing unprecedented insights into the galaxy's true nature. Webb's infrared vision can peer through cosmic dust that obscures visible light, revealing hidden star formation regions, ancient stellar populations, and the intricate structure of the galaxy's spiral arms. These observations are showing us that Andromeda is even more complex and dynamic than we previously realized. One of the most remarkable discoveries about Andromeda's size comes from studying its stellar halo, the sparse collection of ancient stars that surrounds the galaxy's main disk. This halo contains some of the oldest stars in the universe, formed when the galaxy was young and still assembling itself from smaller building blocks. These ancient stars serve as fossil records of Andromeda's early history, and their distribution tells us about the galaxy's growth over billions of years. The stellar halo extends far beyond the visible galaxy, creating a tenuous sphere of stars that may reach as far as 600,000 light-years from Andromeda's center. Within this halo, astronomers have discovered dozens of stellar streams, long, thin trails of stars that were torn from smaller galaxies as they fell into Andromeda's gravitational embrace. These streams are like cosmic archaeological sites, preserving evidence of ancient galactic collisions and mergers that helped build Andromeda into the massive galaxy we see today. Each stellar stream tells a story of cosmic violence and creation. When a smaller galaxy ventures too close to Andromeda, the larger galaxy's immense gravity begins to pull it apart, stretching it into long tendrils of stars that can extend for hundreds of thousands of light-years. The giant stellar stream, one of the most prominent features in Andromeda's halo, stretches across more than 100 degrees of sky as seen from Earth. That's equivalent to the width of 200 full moons placed side by side. The discovery of these stellar streams has fundamentally changed our understanding of how large galaxies like Andromeda grow and evolve. Rather than forming in isolation, galaxies are built through a process called hierarchical assembly, where smaller galaxies merge together over cosmic time to create larger structures. Andromeda bears the scars of this violent history in the form of stellar streams, disrupted satellite galaxies, and warped structures that speak to billions of years of cosmic collisions. The scale of these ancient mergers is almost impossible to comprehend. Some of the stellar streams in Andromeda's halo are the remnants of galaxies that contained billions of stars, entire stellar cities that were torn apart and absorbed by Andromeda's relentless gravity. The process of galactic cannibalism that created modern Andromeda involved the destruction and assimilation of dozens, perhaps hundreds, of smaller galaxies over the course of cosmic history. When we consider the three-dimensional structure of Andromeda, its size becomes even more impressive. The galaxy isn't just a flat disk of stars, it's a complex, layered structure with multiple components. The central bulge rises above and below the main disk like a cosmic football, containing some of the galaxy's oldest and most metal-rich stars. The disk itself has multiple layers with younger, bluer stars concentrated in the spiral arms and older, redder stars filling the spaces between. The thick disk component of Andromeda extends several thousand light-years above and below the main stellar disk, containing stars with a wide range of ages and compositions. This thick disk is thought to be the result of ancient galactic mergers that heated up the stellar orbits and puffed up the galaxy's structure. The thin disk, where most of the galaxy's current star formation occurs, is embedded within this thicker component like a cosmic crepe within a stellar souffle. Recent studies using data from the Gaia Space Telescope have revealed that Andromeda's structure is even more complex than previously thought. The galaxy shows evidence of multiple stellar populations with different kinematics, different patterns of motion through space. Some stars orbit in the same direction as the galaxy's rotation, while others follow more chaotic paths that suggest they were acquired through mergers with smaller galaxies. The rotation of Andromeda itself adds another dimension to its impressive scale. The galaxy spins like a cosmic pinwheel, but different parts rotate at different speeds. Stars near the center complete their orbits in just a few million years, while stars in the outer regions take hundreds of millions of years to complete a single circuit around the galactic center. This differential rotation helps maintain the galaxy's spiral structure and drives the complex dynamics that shape its evolution. The magnetic field of Andromeda provides yet another way to appreciate the galaxy's enormous scale. Like most spiral galaxies, Andromeda is threaded with magnetic field lines that extend throughout its structure. These magnetic fields, though incredibly weak by terrestrial standards, play important roles in star formation, cosmic ray propagation, and the dynamics of interstellar gas. The magnetic field lines trace out the galaxy's spiral structure and extend far into the halo, creating an invisible skeleton that helps organize the galaxy's matter and energy. Radio telescopes have been instrumental in mapping Andromeda's magnetic field structure. The Very Large Array in New Mexico and other radio observatories have detected synchrotron radiation, light emitted by high-energy electrons spiraling around magnetic field lines throughout Andromeda's disk and halo. These observations reveal that the galaxy's magnetic field is organized on scales of hundreds of thousands of light-years, creating a coherent structure that spans the entire galaxy. The interstellar medium will keep us within Andromeda. The gas and dust that fills the space between stars also contributes to our understanding of the galaxy's true size. This material, though incredibly tenuous by terrestrial standards, contains a significant fraction of the galaxy's normal matter. Vast clouds of hydrogen gas extend throughout Andromeda's disk and beyond, providing the raw material for future generations of stars. The 21-centimeter radio emission from neutral hydrogen has allowed astronomers to map the distribution of gas throughout Andromeda with remarkable precision. These observations reveal that the galaxy's gas disk extends even farther than its stellar disk, reaching out to distances of nearly 300,000 light-years from the galactic center. This extended gas disk shows that Andromeda is still actively accreting material from its surroundings, growing larger even as we observe it. The temperature structure of Andromeda's interstellar medium adds another layer of complexity to the galaxy's enormous scale. The gas exists in multiple phases with vastly different temperatures and densities. Cold molecular clouds with temperatures just a few degrees above absolute zero coexist with hot, ionized gas heated to millions of degrees by stellar winds and supernova explosions. This multi-phase structure creates a complex ecosystem that regulates star formation and chemical evolution throughout the galaxy. X-ray observations from telescopes like Chandra and xmm have revealed the hot gas component of Andromeda's interstellar medium. This superheated gas, invisible to optical telescopes, fills much of the galaxy's halo and extends far beyond the visible stellar disk. The hot gas halo may contain as much mass as all the stars in the galaxy combined, representing a significant reservoir of material that could fuel future star formation or be expelled into intergalactic space. The chemical composition of Andromeda provides another fascinating perspective on the galaxy's immense scale and complex history. Unlike our Milky Way, where we can study individual stars in great detail, Andromeda's distance of 2.5 million light-years means we can only analyze the integrated light from millions of stars at once. Yet even this averaged light tells an incredible story of cosmic evolution spanning billions of years and involving the nuclear furnaces of countless stellar generations. Spectroscopic observations of different regions within Andromeda reveal a galaxy-wide gradient in chemical composition. The central regions are enriched with heavy elements, what astronomers call metals, forged in the cores of massive stars and distributed through supernova explosions. As we move outward from the galactic center, the metallicity gradually decreases, reflecting the inside-out growth pattern that characterizes large spiral galaxies like Andromeda. This chemical gradient extends across the galaxy's entire 220,000 light-year diameter, representing one of the largest coherent structures in the local universe. The fact that we can trace systematic changes in stellar composition across such vast distances speaks to the remarkable organizational power of gravity and the long-term stability of galactic structures. Stars that formed in Andromeda's outer regions 10 billion years ago still retain the chemical signatures of their birth, creating a fossil record of galactic evolution written in starlight. The star formation history of Andromeda reveals the galaxy's growth over cosmic time. Unlike our Milky Way, which has maintained a relatively steady rate of star formation throughout its history, Andromeda shows evidence of a more dramatic past. The galaxy appears to have experienced a major burst of star formation several billion years ago, possibly triggered by a significant merger with another large galaxy. This ancient starburst created many of the stars we see in Andromeda's bulge today and may have fundamentally reshaped the galaxy's structure. The evidence for this ancient starburst comes from careful analysis of the colors and brightnesses of stars in different parts of the galaxy. Older stellar populations appear redder because they lack the hot blue stars that die quickly, while younger populations retain their blue color from recently formed massive stars. By mapping these color variations across Andromeda's enormous disk, astronomers can reconstruct the galaxy's star formation history with remarkable precision. The globular cluster system of Andromeda provides another window into the galaxy's vast scale and ancient history. Globular clusters are dense collections of hundreds of thousands of old stars bound together by gravity into spherical structures that can survive for billions of years. Andromeda hosts approximately 500 globular clusters, more than 3 times the number found in our Milky Way, distributed throughout the galaxy's halo in a roughly spherical pattern. These globular clusters serve as test particles that trace the galaxy's gravitational field and dark matter distribution. Their orbits, which can extend hundreds of thousands of light-years from the galactic center, provide crucial information about the total mass and structure of Andromeda. Some of these clusters follow highly elliptical orbits that take them from the galaxy's central regions to the very edge of its halo and back again, completing circuits that last hundreds of millions of years. The most distant globular clusters in Andromeda's system orbit at distances exceeding 400,000 light-years from the galactic center, farther than the distance between the Milky Way and its largest satellite galaxy, the Large Magellanic Cloud. These remote clusters are barely bound to Andromeda by gravity, yet they've remained part of the galaxy's retinue for billions of years, testament to the enormous gravitational reach of this galactic giant. Recent discoveries have revealed that Andromeda's globular cluster system shows clear evidence of accretion from smaller galaxies. Many clusters appear to be organized into streams and groups that trace the orbits of disrupted satellite galaxies. This provides direct evidence that Andromeda has grown through the cannibalization of smaller systems, incorporating not just their stars, but also their globular cluster populations. The dark matter halo of Andromeda represents perhaps the most mysterious aspect of the galaxy's enormous scale. This invisible component, detectable only through its gravitational effects, may contain 10 times more mass than all the visible stars and gas combined. The dark matter halo extends far beyond the visible galaxy, creating a gravitational well that influences the motion of objects across millions of light years. Computer simulations of galaxy formation suggest that Andromeda's dark matter halo may extend as far as 1 million light-years from the galactic center, creating a sphere of gravitational influence larger than the distance between the Milky Way and Andromeda themselves. Within this vast halo, substructures of dark matter, the remnants of smaller halos that merged with Andromeda over cosmic time, continue to orbit and gradually dissolve, adding their mass to the growing giant. The interaction between Andromeda's dark matter halo and that of the Milky Way is already beginning, even though the galaxies themselves won't collide for another 4.5 billion years. The outer edges of these enormous dark matter structures may already be touching, creating subtle gravitational influences that affect the motion of satellite galaxies and stellar streams in both systems. Understanding the true extent of Andromeda's dark matter halo requires sophisticated observational techniques and theoretical modeling. Astronomers use the motions of satellite galaxies, stellar streams, and globular clusters as tracers of the underlying gravitational field. By measuring how these objects move through space, they can infer the distribution of dark matter that must be present to explain their observed motions. The results of these studies are remarkable. Andromeda's total mass, including dark matter, may exceed 2 trillion times the mass of our Sun. This makes it one of the most massive galaxies in the local group and places it among the largest galaxies in the nearby universe. The galaxy's gravitational influence extends across a volume of space containing over 4 million cubic light-years, a domain so vast that light takes over 1 million years to cross from one side to the other. The environmental context of Andromeda adds yet another dimension to its impressive scale. The galaxy doesn't exist in isolation but is part of the local group, a collection of over 80 galaxies bound together by gravity. Andromeda dominates this group, containing more mass than all other local group galaxies combined. Its gravitational influence shapes the orbits and evolution of smaller galaxies across a region spanning several million light-years. The local group itself is part of an even larger structure called the Virgo supercluster, which contains thousands of galaxies organized into clusters and groups. Within this vast cosmic web, Andromeda stands out as one of the largest and most massive individual galaxies, a true giant among giants. The galaxy's enormous size and mass make it a significant player in the large-scale structure of the universe, influencing the motion and evolution of matter across truly cosmic scales. Recent observations with the Hubble Space Telescope have revealed that Andromeda is surrounded by a vast corona of hot gas that extends far beyond the visible galaxy. This corona, heated to temperatures of millions of degrees, may contain as much mass as all the stars in the galaxy. The corona extends to distances of at least 600,000 light-years from the galactic center, creating an enormous reservoir of material that could fuel future star formation or be expelled into intergalactic space. The discovery of Andromeda's hot gas corona has important implications for our understanding of galaxy evolution and the cosmic web. This hot gas represents a significant fraction of the normal matter in the universe, much of which has been missing from previous astronomical surveys. The corona may be fed by gas flowing in from the cosmic web along dark matter filaments, providing a continuous supply of material to fuel the galaxy's ongoing evolution. The cosmic web connection to Andromeda reveals how this galactic giant fits into the universe's largest structures. Dark matter simulations show that galaxies like Andromeda form at the intersections of cosmic filaments, vast streams of dark matter and gas that connect galaxy clusters across hundreds of millions of light-years. These filaments channel material toward massive galaxies, feeding their growth over billions of years and helping to explain how structures as enormous as Andromeda can exist. The Millennium simulation and other large-scale computer models of cosmic evolution show that galaxies of Andromeda's size are relatively rare in the universe. Only about 1 in 10,000 galaxies reaches such enormous proportions, making Andromeda a true cosmic heavyweight. The galaxy's size places it in the top 1% of all galaxies by mass, a distinction that reflects both its fortunate location in the cosmic web and its successful history of merging with smaller systems. This rarity makes our proximity to Andromeda all the more remarkable. The fact that we live next door to one of the universe's largest galaxies is either an extraordinary coincidence or evidence that massive galaxies like Andromeda create favorable conditions for the formation of smaller galaxies like our own Milky Way. The gravitational influence of Andromeda may have helped shape the local group's structure and influenced the formation of our own galactic home. The future evolution of Andromeda adds another fascinating dimension to its already impressive scale. Computer simulations of the galaxy's collision with the Milky Way show that the merged system, sometimes called Milkomeda, will be even larger than either galaxy is today. The combined system may span over 300,000 light-years and contain over 2 trillion stars, making it one of the largest elliptical galaxies in the local universe. But this future merger is still billions of years away, and Andromeda continues to grow even now. The galaxy is actively accreting material from its surroundings, pulling in gas from the intergalactic medium and occasionally capturing smaller galaxies that venture too close. This ongoing growth means that Andromeda is actually getting larger as we observe it, though the changes occur so slowly that they're imperceptible on human timescales. The rate of Andromeda's growth can be estimated by studying the galaxy's current star formation rate and gas accretion. The galaxy is forming new stars at a rate of approximately 1 solar mass per year, meaning that every year enough gas is converted into stars to equal the mass of our Sun. While this might seem modest compared to some starburst galaxies, the steady accumulation of new stars over millions and billions of years contributes significantly to Andromeda's ever-increasing size and mass. The stellar populations within Andromeda reveal the galaxy's complex assembly history, written in the ages and compositions of its trillion stars. The oldest stars, found primarily in the galactic halo and central bulge, formed over 12 billion years ago when the universe was less than 2 billion years old. These ancient stars are metal-poor, containing only the light elements produced in the Big Bang, plus small amounts of heavier elements forged in the first generation of massive stars. In contrast, the youngest stars in Andromeda's spiral arms are metal-rich, containing the accumulated products of billions of years of stellar nucleosynthesis. These stars formed from gas that had been enriched by countless previous generations of stars, each contributing their nuclear ashes to the interstellar medium through stellar winds and supernova explosions. The chemical evolution of Andromeda thus represents a galaxy-wide experiment in stellar alchemy that has been running for over 12 billion years. The spatial distribution of these different stellar populations provides a three-dimensional map of Andromeda's assembly history. The metal-poor halo stars trace the galaxy's early formation, from the collapse of primordial gas clouds, while the metal-rich disk stars record the later phases of evolution dominated by gas accretion and star formation. The intermediate age, thick disk population tells the story of ancient mergers that heated stellar orbits and puffed up the galaxy's structure. Recent advances in stellar archaeology, the study of ancient stars to understand galactic history, have revealed that Andromeda experienced a major merger event approximately 2 billion years ago. This collision with a galaxy roughly 1/4 the mass of the Milky Way fundamentally reshaped Andromeda's structure, triggering a burst of star formation and creating many of the stellar streams we observe in the galaxy's halo today. The evidence for this ancient merger comes from careful analysis of stellar motions and chemical compositions throughout Andromeda. Stars that formed before the merger show different kinematic properties than those formed afterward, creating a clear temporal boundary in the galaxy's stellar populations. This merger event may have been responsible for transforming Andromeda from a smaller spiral galaxy into the massive elliptical spiral hybrid we see today. The supermassive black hole at Andromeda's center provides another perspective on the galaxy's enormous scale. With a mass of approximately 140 million solar masses, this gravitational monster is among the most massive black holes in the local universe. The black hole's sphere of influence, the region where its gravity dominates stellar motions, extends about 13 light-years from the galactic center, encompassing a volume that could contain thousands of solar systems. Yet even this supermassive black hole is dwarfed by the galaxy that surrounds it. The black hole contains only about 1,000th of 1% of Andromeda's total stellar mass, illustrating the vast scale difference between even the most extreme objects and the galaxies that host them. The relationship between black hole mass and galaxy mass appears to be fundamental to galaxy evolution, with larger galaxies hosting more massive central black holes in a tight correlation that extends across cosmic scales. The accretion disk around Andromeda's central black hole, while invisible to optical telescopes, can be detected through its X-ray and radio emissions. This disk of superheated gas spiraling into the black hole extends only a few light hours from the event horizon, a tiny fraction of the galaxy's overall size. Yet the energy released by this accretion process can influence star formation and gas dynamics throughout the galaxy's central regions, demonstrating how processes on the smallest scales can have galaxy-wide consequences. The jets and outflows from Andromeda's central black hole, while currently relatively weak, may have been much more powerful in the past. Radio observations reveal faint lobes of emission extending several thousand light-years from the galactic center, suggesting that the black hole was more active in earlier epochs. These ancient outflows may have played a role in regulating star formation and shaping the galaxy's evolution over cosmic time. The planetary systems within Andromeda represent perhaps the most mind-boggling aspect of the galaxy's scale. If even a small fraction of Andromeda's trillion stars host planetary systems, we're looking at potentially hundreds of billions of worlds within this single galaxy. These planets would span an enormous range of types, sizes, and environments, from scorching hot Jupiters orbiting close to their stars to frozen super-Earths in the outer reaches of planetary systems. The diversity of stellar types within Andromeda suggests an equally diverse population of planetary systems. The galaxy contains everything from young, hot blue giants to ancient, cool red dwarfs, each creating different conditions for planet formation and evolution. Some planetary systems in Andromeda may be billions of years older than our own solar system, potentially hosting civilizations that have had eons to develop and spread throughout their local stellar neighborhoods. The sheer number of potentially habitable worlds within Andromeda is staggering to contemplate. If we assume that 1 in 1,000 stars hosts an Earth-like planet in the habitable zone, a conservative estimate based on recent exoplanet discoveries, Andromeda could contain over 1 billion Earth-like worlds. Each of these planets represents a potential laboratory for the development of life, chemistry, and perhaps even intelligence on scales we can barely imagine. The temporal dimension of Andromeda's existence adds yet another layer to its overwhelming scale. This galaxy has been shining in space for over 12 billion years, nearly as long as the universe itself has existed. To put this in perspective, when Andromeda was already a mature galaxy with billions of stars, our solar system didn't even exist. The galaxy has witnessed the birth and death of countless stellar generations, the formation and destruction of planetary systems, and the slow dance of cosmic evolution across eons that dwarf human comprehension. During Andromeda's lifetime, the universe has expanded significantly, carrying distant galaxies ever farther away and gradually cooling the cosmic background radiation left over from the Big Bang. The galaxy has served as a cosmic lighthouse, its light traveling across the void to reach telescopes on Earth and other worlds throughout the local group. Every photon we detect from Andromeda began its journey in the nuclear furnace of a distant star, carrying information about conditions in that galaxy across millions of years of travel time. The light we see from Andromeda tonight actually left the galaxy 2.5 million years ago, when our earliest human ancestors were just beginning to walk upright on the African savanna. The photons hitting our eyes or telescopes have been traveling through space since before the ice ages, before human civilization, before our species even existed in its modern form. In a very real sense, we're seeing Andromeda as it was in the deep past, a cosmic time machine that reveals the galaxy's ancient history. This light travel time effect means that different parts of Andromeda appear to us as they existed at slightly different times. Light from the galaxy's near side reaches us about 100,000 years before light from the far side, creating a subtle, temporal gradient across the galaxy's face. While this time difference is negligible compared to the galaxy's age, it reminds us that even our observations of nearby cosmic objects are glimpses into the past rather than real-time views of the present. The energy output of Andromeda is as impressive as its size. The galaxy radiates approximately 25 billion times more energy than our Sun, powered by the nuclear fusion occurring in the cores of its trillion stars. This energy output has remained relatively constant for billions of years, making Andromeda one of the most stable and long-lived power sources in the universe. The total energy radiated by the galaxy over its lifetime exceeds the rest mass energy of millions of solar masses, representing an almost incomprehensible release of nuclear energy. The infrared emission from Andromeda, detected by space telescopes like Spitzer and Herschel, reveals the galaxy's hidden star formation activity. Dust grains throughout the galaxy absorb ultraviolet and visible light from young stars and re-emit this energy at longer infrared wavelengths. These observations show that Andromeda is still actively forming new stars, though at a much lower rate than during its peak star formation epoch several billion years ago. The radio emission from Andromeda provides yet another window into the galaxy's enormous scale and complex physics. Synchrotron radiation from high-energy electrons spiraling around magnetic field lines traces the galaxy's magnetic structure across its entire disk. Pulsars, rapidly rotating neutron stars, scattered throughout the galaxy, emit regular radio pulses that can be detected across intergalactic distances. These cosmic lighthouses serve as precise clocks that help astronomers study the galaxy's structure and the properties of the interstellar medium. The gamma-ray emission from Andromeda, detected by the Fermi Gamma-ray Space Telescope, reveals the galaxy's most energetic processes. High-energy photons are produced by cosmic ray interactions, pulsar wind nebulae, and possibly even dark matter annihilation in the galaxy's dense central regions. These gamma rays carry information about the most extreme physics occurring within Andromeda, from the acceleration of particles to near-light speed to the potential signatures of exotic matter. The neutrino flux from Andromeda represents perhaps the most elusive aspect of the galaxy's energy output. These nearly massless particles produced in stellar cores and supernova explosions stream through space at nearly the speed of light, carrying information about nuclear processes deep within the galaxy. While individual neutrinos from Andromeda are impossible to detect with current technology, the cumulative neutrino flux from the galaxy's trillion stars represents a significant component of the cosmic neutrino background. The gravitational wave signature of Andromeda provides a completely new way to study the galaxy's most extreme objects. Binary black holes, neutron star mergers, and other cataclysmic events within the galaxy produce ripples in space-time that propagate outward at the speed of light. While current gravitational wave detectors like LIGO and Virgo are not sensitive enough to detect individual events from Andromeda, future space-based detectors may be able to observe the galaxy's gravitational wave background. The chemical evolution of Andromeda over cosmic time represents one of the largest scale experiments in nuclear physics ever conducted. The galaxy began with only hydrogen and helium, the light elements produced in the Big Bang, and has gradually enriched its interstellar medium with heavier elements through billions of years of stellar nucleosynthesis. This process has created the carbon, oxygen, silicon, iron, and other elements necessary for rocky planets and biological chemistry. The metallicity gradient across Andromeda's disk tells the story of this chemical evolution in exquisite detail. The central regions, where star formation began earliest and proceeded most rapidly, show the highest concentrations of heavy elements. The outer regions, where star formation started later and proceeded more slowly, retain more of their primordial composition. This gradient extends across the galaxy's entire 220,000 light-year diameter, creating one of the largest coherent chemical structures in the universe. The dust content of Andromeda provides another measure of the galaxy's chemical evolution and current star formation activity. Dust grains, composed primarily of carbon and silicate materials, form in the atmospheres of evolved stars and are dispersed into the interstellar medium through stellar winds and supernova explosions. The total dust mass in Andromeda is estimated at approximately 100 million solar masses, enough material to build 1 million Earth-sized planets. This dust plays crucial roles in the galaxy's ongoing evolution. It absorbs ultraviolet radiation from young stars, protecting molecular clouds from photodissociation and enabling the formation of complex molecules. It provides condensation nuclei for the formation of larger particles and eventually planetesimals in protoplanetary disks, and it serves as a coolant for the interstellar medium, radiating away thermal energy and allowing gas clouds to collapse and form new stars. The molecular content of Andromeda reveals the galaxy's capacity for chemical complexity on truly cosmic scales. Radio telescopes have detected dozens of different molecular species in the galaxy's interstellar medium, from simple diatomic molecules like carbon monoxide to complex organic compounds containing dozens of atoms. The total molecular mass in Andromeda may exceed 1 billion solar masses, representing an enormous reservoir of chemically processed material. These molecules form on the surfaces of dust grains in the cold, dense regions of molecular clouds. The chemistry occurs slowly, over timescales of millions of years, but the sheer volume of space involved means that Andromeda is continuously producing vast quantities of complex molecules. Some of these molecules, including amino acids and other prebiotic compounds, could serve as the building blocks for life if they become incorporated into planetary systems. The magnetic field structure of Andromeda extends the galaxy's influence far beyond its visible boundaries. Magnetic field lines, though invisible to optical telescopes, thread through the galaxy's entire volume and extend into the surrounding intergalactic medium. These fields play crucial roles in star formation, cosmic ray propagation, and the dynamics of the interstellar medium. The total magnetic energy stored in Andromeda's field may be equivalent to the rest mass energy of thousands of solar masses. The cosmic ray population within Andromeda represents another form of the galaxy's extended influence. High-energy particles accelerated by supernova shocks, pulsar winds, and other violent processes stream throughout the galaxy and beyond, carrying energy and momentum across vast distances. The cosmic ray pressure in Andromeda may be sufficient to drive galactic winds that expel gas from the galaxy's gravitational well, regulating star formation and chemical evolution on galaxy-wide scales. The tidal forces exerted by Andromeda extend across millions of light-years, influencing the structure and evolution of the entire local group. These gravitational effects are already beginning to distort the outer regions of our own Milky Way, stretching stellar streams and satellite galaxies in directions that point toward our massive neighbor. The Magellanic Stream, a trail of gas stripped from the large and small Magellanic Clouds, may be partially influenced by Andromeda's distant gravitational pull, demonstrating how the galaxy's influence extends far beyond its visible boundaries. Computer simulations of the local group's evolution show that Andromeda's gravitational dominance has been shaping our cosmic neighborhood for billions of years. Smaller galaxies throughout the region follow complex orbits that are influenced by both the Milky Way and Andromeda, creating a dynamic system where galactic interactions occur across vast distances and timescales. Some of these smaller galaxies may eventually be captured by Andromeda, adding their stars and gas to the already enormous galaxy. The approaching collision between Andromeda and the Milky Way provides a unique opportunity to study galactic dynamics on the largest possible scales. Current observations show that the two galaxies are approaching each other at approximately 250,000 miles per hour, but this speed is gradually increasing as their mutual gravitational attraction grows stronger. The collision, expected to begin in approximately 4.5 billion years, will unfold over several billion years as the galaxies merge and settle into a new equilibrium. During this cosmic collision, the combined gravitational forces will trigger massive bursts of star formation as gas clouds throughout both galaxies are compressed and heated. The supermassive black holes at the centers of both galaxies will eventually merge, creating a single black hole with a mass exceeding 200 million times that of our Sun. The resulting galaxy, sometimes called Milkomeda, will be one of the largest elliptical galaxies in the local universe, with a diameter potentially exceeding 400,000 light-years. The stellar dynamics during this merger will be incredibly complex, with computer simulations requiring some of the world's most powerful supercomputers to model accurately. Individual stars will follow chaotic orbits as they respond to the changing gravitational field, but direct stellar collisions will be extremely rare due to the vast distances between stars. Instead, the merger will primarily involve the redistribution of stellar orbits and the mixing of the two galactic populations. The environmental impact of Andromeda's enormous size extends to its effects on the cosmic web and large-scale structure formation. The galaxy's massive dark matter halo creates a significant gravitational well that influences the flow of matter across tens of millions of light-years. Gas streams in the cosmic web are deflected by Andromeda's gravity, potentially affecting the formation and evolution of galaxies throughout the local supercluster. Recent studies of the local cosmic web have revealed that Andromeda sits at the intersection of several dark matter filaments, explaining how the galaxy was able to grow to such enormous size. These filaments channel matter toward the galaxy from vast distances, providing a continuous supply of gas and smaller galaxies that fuel Andromeda's ongoing growth. The galaxy's position in this cosmic infrastructure makes it a natural gathering point for matter in our region of the universe. The observational challenges posed by Andromeda's size have driven the development of new astronomical techniques and technologies. Mapping the galaxy's full extent requires wide-field surveys that can cover large areas of sky while maintaining sufficient sensitivity to detect faint stellar populations. The Panoramic Survey Telescope and Rapid Response System, the Dark Energy Survey, and other large-scale projects have been essential for revealing the galaxy's true boundaries and structure. Future space missions will provide even more detailed views of Andromeda's enormous scale. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will have the sensitivity and field of view needed to map stellar populations throughout Andromeda's halo with unprecedented precision. The extremely large telescope, currently under construction in Chile, will be able to resolve individual stars in Andromeda's outer regions, providing new insights into the galaxy's structure and history. The technological requirements for studying Andromeda illustrate the galaxy's impact on human scientific endeavor. Detecting faint stellar streams in the galaxy's halo requires cameras with billions of pixels and exposure times lasting hours. Measuring the motions of individual stars across such vast distances demands astrometric precision better than a milliarc second, equivalent to measuring the width of a human hair from a distance of 1,000 miles. The data storage and processing requirements for Andromeda studies are equally impressive. A single deep image of the galaxy can contain terabytes of information, and comprehensive surveys generate petabytes of data that must be processed, analyzed, and archived for future generations of astronomers. The computational challenges of modeling Andromeda's structure and evolution require supercomputers capable of tracking the motions of billions of particles over cosmic timescales. The educational impact of Andromeda's scale extends far beyond professional astronomy. The galaxy serves as a perfect example for teaching concepts of distance, time, and scale that are fundamental to understanding our place in the universe. Students who grasp the true size of Andromeda gain an appreciation for cosmic scales that transforms their perspective on Earth, the solar system, and human existence itself. The philosophical implications of Andromeda's enormous size challenge our understanding of significance and meaning in the universe. A galaxy containing 1 trillion stars and potentially billions of planetary systems forces us to confront questions about the uniqueness of Earth and the prevalence of life in the cosmos. If even a tiny fraction of Andromeda's stars host habitable planets, the galaxy could contain more living worlds than there are people on Earth. The cultural impact of Andromeda extends beyond science into art, literature, and human imagination. The galaxy has inspired countless works of science fiction, from novels about intergalactic travel to films depicting cosmic civilizations. The knowledge that such an enormous structure exists in our cosmic neighborhood has fundamentally changed how humans see themselves in relation to the universe. The economic implications of studying Andromeda reflect the galaxy's role in driving technological innovation. The instruments and techniques developed for galactic astronomy have found applications in fields ranging from medical imaging to national security. The computational methods used to model galaxy formation have contributed to advances in weather prediction, climate modeling, and artificial intelligence. The international cooperation required for Andromeda research demonstrates how the galaxy's scale transcends national boundaries and brings together scientists from around the world. Major observatories and space missions involve collaborations between dozens of countries, sharing the costs and benefits of exploring our cosmic neighborhood. The galaxy serves as a unifying focus for human scientific endeavor, reminding us that some questions are too large for any single nation to answer alone. The timeline for understanding Andromeda's full scale spans multiple human generations. Many of the astronomers who began studying the galaxy in the mid-20th century did not live to see the recent discoveries about its true extent. Similarly, Current research programs will likely require decades to complete, with results that will inform and inspire future generations of scientists and space enthusiasts. The preservation of Andromeda observations for future study represents a significant challenge in data archiving and curation. Digital images and spectra from the galaxy must be stored in formats that will remain accessible as technology evolves, ensuring that future astronomers can build upon current discoveries. The accumulated observations of Andromeda represent one of humanity's most detailed records of a cosmic object, a scientific legacy that will endure long after current telescopes become obsolete. The legacy of Andromeda research extends beyond pure science into the realm of human heritage and cosmic perspective. Every photograph of the galaxy, every measurement of its stellar populations, every discovery about its structure contributes to humanity's growing understanding of our place in the cosmic hierarchy. The galaxy serves as a constant reminder that we inhabit a universe of almost incomprehensible scale and beauty, where structures containing trillions of stars exist as single objects in an even vaster cosmic web. The technological spin-offs from Andromeda research have revolutionized fields far removed from astronomy. The charge-coupled devices originally developed for astronomical imaging now form the heart of digital cameras and medical imaging systems. The image processing algorithms used to enhance faint stellar features have found applications in satellite reconnaissance and medical diagnostics. The statistical methods developed for analyzing galactic structure have contributed to advances in data mining and machine learning. The precision timing systems required for coordinating observations of Andromeda across multiple telescopes have driven improvements in atomic clocks and global positioning systems. The error correction codes used to transmit data from space-based observatories have enhanced the reliability of internet communications and digital storage systems. The adaptive optic systems that compensate for atmospheric turbulence in ground-based telescopes have inspired new approaches to laser surgery and optical manufacturing. The materials science advances driven by Andromeda observations have produced innovations in everything from spacecraft construction to consumer electronics. The ultra-low noise detectors needed to capture faint light from the galaxy's outer regions have led to improvements in night vision systems and medical sensors. The lightweight mirror technologies developed for space telescopes have found applications in solar concentrators and optical communication systems. The computational challenges of modeling Andromeda's evolution have pushed the boundaries of high-performance computing and numerical simulation. The N-body codes used to track the motions of millions of stars and dark matter particles have contributed to advances in weather prediction, climate modeling, and fluid dynamics. The parallel processing techniques developed for galactic simulations have enhanced the efficiency of everything from financial modeling to pharmaceutical research. The data visualization methods created to display Andromeda's complex three-dimensional structure have revolutionized how scientists in many fields present and interpret their results. The false color imaging techniques that reveal different stellar populations have found applications in medical imaging and remote sensing. The interactive software tools that allow astronomers to explore galactic data have inspired new approaches to scientific education and public outreach. The international collaboration required for major Andromeda research projects has served as a model for addressing other global challenges. The protocols developed for sharing telescope time and coordinating observations have influenced international agreements on climate monitoring and space exploration. The data-sharing standards established for galactic surveys have contributed to open science initiatives in fields ranging from genomics to particle physics. The educational programs inspired by Andromeda research have introduced millions of students to concepts of scale, time, and scientific methodology. Planetarium shows featuring the galaxy have sparked interest in astronomy and physics among countless young people. The citizen science projects that engage volunteers in classifying galactic features have demonstrated the power of public participation in scientific research. The philosophical questions raised by Andromeda's enormous scale continue to influence human thought about consciousness, meaning, and purpose in the universe. The galaxy's trillion stars and potential billions of planets force us to confront the possibility that intelligence and civilization may be common in the cosmos. This perspective challenges anthropocentric worldviews and encourages a more humble and interconnected understanding of humanity's role in the universe. The artistic inspiration drawn from Andromeda's beauty and scale has enriched human culture in countless ways. Painters have attempted to capture the galaxy's spiral structure and ethereal glow. Musicians have composed symphonies inspired by the cosmic dance of its stellar populations. Writers have crafted stories that explore the implications of such vast structures for the future of human civilization. The spiritual significance of Andromeda varies across cultures and belief systems, but the galaxy consistently evokes feelings of awe, wonder, and transcendence. Many people find that contemplating the galaxy's scale provides perspective on daily concerns and connects them to something larger than themselves. The galaxy serves as a natural cathedral, inspiring reverence for the beauty and complexity of the natural world. The future exploration of Andromeda will likely involve technologies that seem like science fiction today. Proposed space-based interferometers could resolve individual stars throughout the galaxy's disk, revealing details about stellar populations and planetary systems. Advanced spectroscopic surveys could map the chemical composition of gas clouds across the galaxy's entire structure. Gravitational wave detectors might eventually detect the signatures of stellar mass black hole mergers throughout Andromeda's volume. The possibility of direct exploration of Andromeda, while currently beyond our technological capabilities, continues to inspire research into advanced propulsion systems and interstellar travel. Even if such missions remain centuries in the future, the galaxy serves as an ultimate destination for human expansion into the cosmos. The knowledge that such an enormous and complex structure exists in our cosmic neighborhood provides a compelling target for future generations of explorers. The search for life within Andromeda represents one of the most profound questions in astrobiology. With potentially billions of planetary systems, the galaxy could host countless forms of life, from simple microorganisms to advanced civilizations. The development of techniques for detecting biosignatures and technosignatures across intergalactic distances could revolutionize our understanding of life's prevalence in the universe. The study of Andromeda's supermassive black hole provides insights into some of the most extreme physics in the universe. The black hole's enormous mass and the complex dynamics of its accretion disk offer natural laboratories for testing theories of general relativity and quantum mechanics. Future observations might detect the gravitational wave signatures of matter falling into the black hole or the effects of frame dragging on nearby stellar orbits. The chemical evolution of Andromeda over cosmic time provides a unique perspective on the universe's transition from simplicity to complexity. The galaxy's stellar populations record the gradual enrichment of the cosmos with heavy elements, the building blocks of rocky planets and biological chemistry. Understanding this process in detail could provide insights into the conditions necessary for the emergence of life and intelligence. The magnetic field structure of Andromeda offers clues about fundamental processes in plasma physics and magnetohydrodynamics. The galaxy's field lines, shaped by stellar winds, supernova explosions, and galactic rotation, create a complex three-dimensional structure that influences everything from cosmic ray propagation to star formation rates. Advanced radio telescopes could map this structure in unprecedented detail, revealing new aspects of galactic physics. The dark matter distribution within Andromeda remains one of the galaxy's greatest mysteries. While we can infer the presence of dark matter from its gravitational effects, its true nature remains unknown. future experiments might detect dark matter particles directly or reveal new physics that explains the galaxy's structure without invoking exotic matter. The resolution of the dark matter puzzle could fundamentally change our understanding of the universe. The environmental impact of Andromeda on the local group continues to unfold as new observations reveal the galaxy's influence on smaller systems. The tidal streams and disrupted satellites throughout the region tell stories of cosmic violence and accretion that span billions of years. Understanding these processes provides insights into how large-scale structure forms and evolves throughout the universe. The cosmic significance of Andromeda extends far beyond its role as our nearest galactic neighbor. The galaxy serves as a crucial benchmark for understanding galaxy formation and evolution throughout the universe. Its well-studied structure, stellar populations and dynamics provide a template for interpreting observations of more distant galaxies, where individual stars cannot be resolved and detailed studies are impossible. Every discovery about Andromeda's properties helps astronomers understand how galaxies like it form and evolve across cosmic time. The galaxy's role in testing cosmological models cannot be overstated. Andromeda's mass, size, and satellite system provide critical constraints on theories of dark matter, dark energy, and the formation of large-scale structure. The galaxy's properties must be consistent with our understanding of how the universe evolved from the smooth conditions of the early cosmos to the complex web of galaxies we observe today. Any discrepancies between theoretical predictions and Andromeda's observed characteristics could signal the need for new physics or modifications to our cosmological models. The precision with which we can measure Andromeda's properties makes it an ideal laboratory for testing fundamental physics. The galaxy's rotation curve, the relationship between orbital velocity and distance from the center, provides one of the clearest demonstrations of dark matter's existence. The precise timing of pulsar signals from within the galaxy could eventually test Einstein's theory of general relativity in the strong field regime. The galaxy's gravitational lensing effects on background objects offer another avenue for probing the nature of gravity and spacetime. The study of stellar evolution within Andromeda provides insights into the life cycles of stars across a wide range of masses and metallicities. The galaxy's diverse stellar populations, from ancient metal-poor halo stars to young metal-rich disk stars, offer natural experiments in stellar physics that cannot be replicated in laboratories. Observations of variable stars, supernovae, and stellar remnants within Andromeda help calibrate our understanding of stellar evolution and nucleosynthesis. The interstellar medium of Andromeda serves as a vast laboratory for studying the physics of gas and dust in space. The galaxy's molecular clouds, H2 regions, and supernova remnants provide examples of astrophysical phenomena under conditions that range from the coldest and most tenuous to the hottest and most dense. Understanding these processes in Andromeda helps astronomers interpret similar phenomena in more distant galaxies where detailed observations are impossible. The star formation history of Andromeda offers crucial insights into how galaxies regulate their growth over cosmic time. The galaxy's current low star formation rate, despite its enormous gas reservoirs, suggests that feedback processes from stars and black holes play important roles in suppressing star formation. Understanding these regulatory mechanisms is essential for explaining why galaxies don't convert all their gas into stars and how they maintain their structure over billions of years. The chemical abundance patterns in Andromeda provide a detailed record of nucleosynthesis processes throughout the galaxy's history. Different elements are produced by different types of stars and stellar explosions, creating unique chemical fingerprints that reveal the relative contributions of various stellar populations. The spatial distribution of these elements across Andromeda's disk and halo tells the story of how metals have been mixed and redistributed throughout the galaxy over cosmic time. The globular cluster system of Andromeda offers a unique perspective on the galaxy's assembly history and the formation of dense stellar systems. These ancient clusters, some of which may be older than the galaxy itself, preserve information about the conditions in the early universe when the first generations of stars were forming. The properties of Andromeda's globular clusters provide constraints on theories of cluster formation and evolution that complement studies of similar systems in our own galaxy. The satellite galaxy population around Andromeda provides insights into the hierarchical assembly of large galaxies and the nature of dark matter on small scales. The number, distribution, and properties of these satellites must be consistent with predictions from cosmological simulations, providing important tests of our understanding of structure formation. Discrepancies between observations and theory could reveal new physics or highlight gaps in our understanding of galaxy formation processes. The approaching merger between Andromeda and the Milky Way offers a unique opportunity to study galactic dynamics in real time. While the collision won't occur for billions of years, astronomers can already observe the early stages of tidal interaction between the two galaxies. Computer simulations of the merger provide predictions that can be tested against future observations, offering insights into the physics of galactic collisions and the formation of elliptical galaxies. The technological challenges of studying Andromeda continue to drive innovations in astronomical instrumentation and data analysis. The galaxy's enormous angular size on the sky requires wide-field telescopes and cameras with billions of pixels. Its faint outer regions demand exquisite sensitivity and careful control of systematic errors. The vast amounts of data generated by Andromeda surveys require sophisticated algorithms for data processing, source detection, and statistical analysis. The citizen science opportunities provided by Andromeda research have engaged thousands of volunteers in the scientific process. Projects like Galaxy Zoo have enlisted public help in classifying galactic features and identifying interesting objects within Andromeda's structure. These collaborations have not only accelerated scientific discovery, but also provided educational opportunities for participants to learn about astronomy and contribute to our understanding of the universe. The cultural impact of Andromeda research extends into popular media, education, and public understanding of science. Documentary films about the galaxy have reached millions of viewers, inspiring interest in astronomy and space science. Educational materials based on Andromeda observations are used in classrooms around the world to teach concepts of scale, time, and scientific methodology. The galaxy's beauty and accessibility make it an ideal ambassador for astronomy and space science. The economic impact of Andromeda research, while difficult to quantify precisely, extends far beyond the direct costs of telescopes and instruments. The technological innovations driven by galactic astronomy have created entire industries and generated economic benefits that far exceed the initial investments. The international collaborations required for major surveys have strengthened scientific partnerships and cultural exchanges between nations. The environmental considerations of Andromeda research highlight the importance of preserving dark skies for astronomical observations. Light pollution from human activities increasingly interferes with observations of faint galactic features, threatening our ability to study the galaxy's outer regions. The protection of astronomical sites and the development of dark sky preserves have become important conservation issues with implications for both scientific research and cultural heritage. The ethical dimensions of Andromeda research touch on questions of resource allocation, international cooperation, and the responsibilities of the scientific community. The enormous costs of major telescopes and space missions raise questions about priorities and the distribution of scientific resources. The potential discovery of life or intelligence within Andromeda would raise profound questions about our responsibilities as cosmic citizens and the ethics of interstellar communication. The long-term preservation of Andromeda data represents a significant challenge for the astronomical community. Digital observations must be archived in formats that will remain accessible as technology evolves, ensuring that future generations can build upon current discoveries. The development of standards for data preservation and the establishment of permanent archives are essential for maintaining the scientific legacy of Andromeda research. The inspiration provided by Andromeda's scale and beauty continues to motivate new generations of scientists, engineers, and explorers. The galaxy serves as a reminder that the universe contains wonders beyond human imagination, and that there are always new frontiers to explore. For many astronomers, the study of Andromeda represents not just a scientific endeavor, but a profound connection to the cosmos and our place within it. The future of Andromeda research promises even more spectacular discoveries as new technologies come online and our understanding of galactic physics deepens. The galaxy will continue to serve as a laboratory for testing theories, a benchmark for understanding cosmic evolution, and a source of inspiration for all who seek to understand our place in the universe. In studying Andromeda, we study ourselves, our origins, our future, and our cosmic significance in a universe of almost unimaginable scale and beauty. If you made this far, I am sure you will love this other video at the left side of the screen. How long would it take us to leave the solar system? You'll discover the mind-blowing truth about where our solar system really ends, explain why even our fastest spacecraft are crawling at a snail's pace compared to the immense distances involved,